Hey everyone. So today we're going to start talking about light, and the reason why we were going to even bother with light is because the quantum mechanical model that we've been studying about lately, basically that new model of the atom that we've been discussing, actually grew from studying light. So light is just a form of electromagnetic radiation, which is just another form of energy, and it's just one of many different parts of radiation that can exist. When we take all of these different forms of radiation, we actually form what's called the electromagnetic spectrum. Right down here, you have all the different types of radiation. So they range from gamma rays, basically your cosmic rays. We've seen these talking about nuclear chemistry, all the way up to X-rays, microwaves, and our long radio waves here. Right here in this middle, we have what's called the visible spectrum. This is our visible light. It's where our colors come from. Now, all forms of electromagnetism travel at the same speed if through a vacuum. This speed, some of you know as the speed of light. It's given as 3.0 times 10 to the 8 meters per second. So, all forms of radiation will move at exactly the same speed. That's why this is referred to as the speed of light constant, because it's always going to be the same as long as you're traveling through a vacuum. Now, a vacuum is just an area where there's nothing in it, no air, nothing. So, when discussing how light moves, light's going to travel like a wave. Okay, so light is energy, and energy travels in waves. Now, waves have three key properties to them. That is the amplitude, the wavelength, and the frequency. So the amplitude is the height of the wave. So you have what's called a crest, the maximum. So when your wave is at zero, the amplitude is just going to be how high that wave is. So you can see right here, it's basically from the bottom where it's at zero all the way up to the top. Okay. The wavelength is the distance between the crests. So the wavelength is the distance between the two peaks here. So the crest is just the peak. Think of it as the maximum on a parabola. So here, the wavelength is the distance between them. Lastly, the frequency is the number of wave cycles per unit time. What that means is the frequency is how many times one cycle of a wave repeats itself over a period of time. By a cycle of a wave, you can basically identify it by marking a spot on it. So if we're talking about a wave cycle, we might consider it from right here until it starts to repeat itself, right here. So the frequency would be how many times this section appears over a period of time. So the frequency and the wavelength of an electromagnetic wave can actually be determined and given by an equation. This equation relates the speed of light to it as well because we're talking about how it travels. So it's given to as c equals to lambda nu. So c again is the speed of light. So again, this is going to be a constant. It's never going to change. Now, this symbol right here, the Greek symbol called nu, that is your frequency. And your lambda symbol here is your wavelength. So we're going to be using Greek symbols here to represent these different quantities, or measurements, sorry. So the speed of light is nothing but the product of the wavelength and the frequency. So let's take a look at a practice problem. So we want to calculate the wavelength of yellow light that's emitted by a sodium lamp if the frequency of the radiation is 5.10 times 10 to the 14 hertz. So hertz, or inverse seconds, as you can see here, seconds to the -1, is the unit for frequency. So if I want to calculate the wavelength here, I know that the wavelength, lambda, and the frequency, nu, are related within this equation. The speed of light equals to lambda nu. If I want to solve for the wavelength, okay, well, we can actually just rearrange this here. We want to solve for lambda. So, sorry, we're just going to go ahead and divide by nu on both sides. And we get that lambda, the wavelength, is equal to c, the speed of light, divided by nu, the frequency. So the speed of light we know as 3.0 times 10 to the 8th meters per second. Your frequency, is equal to 5.10 times 10 to the 14 hertz, or inverse seconds. That's what we're going to use here. So hertz you're probably more familiar with when it comes to like TVs, right? Certain TVs have a certain like frequency to them. That's the refresh rate of it. If you're into like electronics and everything like that, but it's basically just telling you how many times that wave is going to repeat itself. So just plugging this information in, lambda is going to equal to 3.0 times 10 to the 8th meters per second divided by 5.10 times 10 to the 14th inverse seconds. So we're going to use that one that we can see how the units are going to cancel out. And doing so gives us 0.588 times 10 to the minus 6. So our unit here, we're going to have meters per second divided by inverse seconds, which ends up actually being meters per second times seconds. Seconds cancel out, and we're left with meters. Meters you're probably more familiar with as a unit for length. Well, wavelength is the length of a wave. So it makes sense that our unit should be in meters. Now we just have to adjust our scientific notation here. 0.588 times 10 to the negative 6 is not the correct notation because this coefficient has to be between 1 and 10. So just moving over that decimal, we get 5.88 times 10 to the negative 7 meters. Typically when we talk about wavelength, we're talking about energy or a wave. This length is usually going to be pretty small. So having a times 10 to the negative 7 for a wavelength is pretty normal, especially when we're talking about meters. The other standard unit that we use for a wavelength is given in nanometers. Okay, so you'll probably be more familiar and you'll see a lot more mentions of nanometers talking about wavelength than you will typically meters, just because the nanometer is a lot more appropriate. That way we don't have to deal with the scientific notation. You'll see a few examples of that when we actually talk about color. So let's get to talking about color. So we know here that there's a range of light that we can actually see called the visible light. So visible light, or white light, is really just a combination of all the different colors. So you've probably seen before when you shine a white light through a glass prism that you get a nice rainbow at the end of it. Well, that's basically taking advantage of what's called spectroscopic analysis. It's where you actually analyze the different spectrum that come from some energy here. So our eyes can actually only see this one little area of the electromagnetic spectrum. That's why it's called the visible light spectrum. So white light is nothing but a combination of all the rainbow colors put together. It's one of the reasons why we get a rainbow whenever it rains, because the water molecules in the air, after it's been raining or while it's raining, actually help do what's called diffracting, which is splitting apart the white light. That's how this glass prism works. It diffracts and it actually breaks it apart into the different rainbow colors. So just a quick little lesson here about how the eye works. So we can only see in this range, if we go back here, between 390 to about 720 nanometers. So when light shines through to our eye, it actually goes back and it hits what's called our retina. In the retina, we have what are called rods and we have cones. The rods are able to pick up the intensity of the light, but they actually don't see any color. The cones are actually the ones that can differentiate the color, and it's differentiated by the wavelength of it. So our cones, basically the structure of our eyes, are only able to really pick up this range of wavelength, about 580 to 720 nanometers. So it's because of this range that we see certain colors and why we can't see other aspects of the electromagnetic spectrum. It's really the wavelength that differentiates the different forms of radiation. So we, again, can only see in this range. Anything outside of it, we can't really see because our eyes have not developed enough for us to see that. So moving on here, just talking about spectroscopy. So different elements actually can produce different forms of a spectrum, and that's because they all have different numbers of electrons. So electrons, we've already seen about how they're related to energy. Well, the electrons, because they're different in every single atom, actually behave differently from each other when exposed to energy, and so different elements produce what's called a different atomic emission spectrum. So that's just basically showing that whole rainbow spectrum, and different parts of that's going to be emphasized. So you can see here that every one of these elements has got different lines here that are really emphasized. The atomic emission spectrum for an element is very unique. It's kind of like a fingerprint for the element. If you go and actually add some light to it or electricity, you can actually see that every element will have its own unique color because it's emitting its own unique spectrum. So the reason why this happens, we're going to take a look at the Bohr model for that. So the Bohr model, we know about these different energy levels that exist. So our electrons are hanging on these energy levels. Well, what happens is you have a nice electron here, and it actually gets hit with some energy. Okay, it enters a process called excitation. So excitation is when this electron then gets excited. It can jump energy levels. So if I have an electron on the first ring, okay, and it gains some energy through some kind of light source or whatever else is given it energy, it can actually move up to a higher energy ring. This is a temporary state called the excited state, because now the electron's excited, it has a lot of energy. But it actually does not belong there, the energy is just borrowed, so the electron will go back to its original ground state. So the ground state is where it actually started. In doing so, the energy that it took in, it emits in a process we call emission. So that energy that it emits, that's the energy that we actually get to see that makes our spectrum. So because of the fact that all these different elements have got different numbers of electrons on different rings and everything, we get different forms of emission, so we get different spectra in the end. So if we take a look here at an energy diagram, this is basically going to be the Bohr model, but without the atom, just taking a look at the different energy levels. So when an electron gets excited, different things can actually happen to it. So we're going to go ahead and to give this one electron some energy, and it's going to jump from our energy level 1 to our energy level 4. So again, this is the process called excitation. It is getting excited. So when it gets to energy level 4, it's in what's called the excited state. This electron is then going to go ahead and release that energy and come crashing right back down, okay, in what's called emission. So it emits that energy. It emits that energy in a form that we're going to discuss later called a photon. So this is actually a process called fluorescence. So you probably heard of like fluorescent dyes and fluorescent colors. Well, fluorescence is when it's a property when an electron is able to absorb light of a short wavelength and then emit light of a different longer wavelength. So it basically, fluorescence, it's just emitting a different energy of the light that it actually absorbed to begin with. When you take away the energy source, whatever substance you have will stop fluorescing, because now there's no more energy to absorb, so there's going to be no excitation and emission process. Another form that we can see, another process called phosphorescence here. Same idea, electrons are going to go ahead, absorb some energy, but this time, instead of going down in just one swoop, okay, in phosphorescence, the electron takes its time. So it may stop off at different energy levels. It's not going to go all the way down immediately. So it's the same process. It's going to absorb light or energy of one wavelength and then emit of a different one. But this process takes much, much longer. So this emission lasts for a very, very long time. And it actually continues when you take away the energy source. So energy sources can be something like a UV lamp, flames, electricity. just something that provides the electron energy to go up to a higher energy state. And this phosphorescence is that when the emission takes over a longer period of time. We know this as the very common term glow in the dark. So you apply some light to something, you take the light away, and it'll keep glowing because it's emitting that light, it's giving up that energy over a longer period of time. Sorry, I will glow in the sun. So glow in the dark things work by a process called phosphorescence. So that is what the scientific name of that process is. Glow in the dark phosphorescence. It is just a longer form of fluorescence. So getting into what's called the photoelectric effect, this is where we really began to study light as different than just being a wave or energy. So in this photoelectric effect, light basically requires a minimum frequency to remove electrons from the surface of a metal. Okay. So what happens is you shine light on some metal. If the frequency reaches a minimum required, it can actually eject electrons. These electrons then go to what's called an anode, which is a positively charged plate. It creates an electrical current, okay? And then that can be used for whatever it is. It is actually how our remotes work. And so it doesn't really matter how long the light is shining for, okay? If it doesn't have a minimum frequency, then it's not going to work. The reason for that lies in the origins of quantum mechanics. So light, rather than being a continuous wave, as we all thought, it's actually broken up into tiny little specific amounts called the quanta. So instead of just being one long wave, we have little packets of light. So it's really not continuous, but it's a pack of energy which we refer to as a quanta. So light, we're going to treat it as a particle, and we're going to call that particle a photon. So a photon is just the particle form of energy. So we've talked already about the particle-wave duality of an electron. Well, we're going to refer that back to light, where light can not only act like a wave, but can act like a particle. And whenever we talk about light's behavior as a particle, we're going to refer to that as a photon. So photons have a different energy to them. The energy is given by this equation right here. E, your energy, which is the product of what's called Planck's constant, right here, times the frequency. So nu makes an appearance again. This is our frequency. So if we know the frequency of a photon, then we know its energy. This is why in the photoelectric effect, we needed a minimum frequency, because that basically meant we needed a minimum energy to release the electrons. So let's take a quick look here. So we want to know what's the energy of a photon of microwave radiation if the frequency is 3.20 times 10 to the negative 11 seconds. So as we just saw, E equals to h nu. Okay, so we're looking for the energy, so our equation set up the way it is. Planck's constant is given as 6.626 times 10 to the negative 34 joule, which is the unit for energy, seconds. And our frequency is given as 3.20 times 10 to the negative 11 inverse seconds. Okay, so our energy is just going to be equal to the product of these two. So it's going to be 6.626 times 10 to the negative 34 joule seconds times 3.20 times 10 to the negative 11 inverse seconds. Okay. Doing so gives you 21.20 times 10 to the negative 45. So our seconds and our inverse seconds cancel out. Joules. Joules is the unit for energy, so we know that the unit checks out. It is matching up what we want. Now again, we just have to go ahead and make a small adjustment here because this is not in proper scientific notation form. Moving that decimal place over, we get 2.120 times 10 to the negative 44 joules. Okay. So if we know the frequency of an electron, it is possible, of a photon, it's possible to find the energy of it. Okay. So going back to particle wave duality, we're going to now apply that to light. So light, as we mentioned before, can act as both a wave, its energy form, and a stream of particles, basically the matter form. Well, Einstein has suggested that if light is going to act like a particle, and particles matter, that means that particle should have some kind of momentum. Then photons should have a momentum. Well, that momentum is equal to Planck's constant over the wavelength here. So our momentum, rho, is equal to h over lambda. Okay. So if we know the wavelength of a photon, we know its momentum. But if we know its momentum, we can then find its wavelength, vice versa. It wasn't until it was further worked on by Louis de Broglie did it get expanded here. So de Broglie realized that since the momentum is equal to the mass times the velocity, you could then rearrange the above equation to get that the wavelength of a photon is equal to Planck's constant divided by its mass times its velocity. So if we know the mass and the velocity of a photon, we can determine its wavelength, and thus we can actually determine its energy. So let's go ahead and just take a look here. So we want to know what is the wavelength of an electron moving at 5.31 times 10 to the 6 meters per second. We're told the mass of an electron is 9.11 times 10 to the negative 31 kilograms, and Planck's constant right here that we just saw before. So we have that our wavelength is equal to h, Planck's constant, divided by mass times velocity. Okay, and again, this is your momentum. So h given as 6.626 times 10 to the negative 34. Again, the unit here, joule seconds. Your mass of the electron, 9.11 times 10 to the negative 31 kilograms. And then our velocity here is 5.31 times 10 to the 6th meters per second. Okay, so our wavelength is then going to be equal to 6.626 times 10 to the negative 34 joule seconds divided by 9.11 times 10 to the negative 31 kilograms times 5.31 times 10 to the 6th meters per second. Just simplifying that a little bit gets us 6.626 times 10 to the negative 34 joule seconds over 4.837 times 10 to the negative 24 kilogram meter seconds per second. Okay, and then simplifying that even more, okay, we get 1.369 times 10 to the negative 10 meters. So here is the wavelength of an electron if it's moving at this velocity and has this mass, which the mass of an electron is constant. So it was thanks to this new equation devised by de Broglie that we actually have a quantum mechanics. So because of the fact that objects at our size, at human size, have a large mass and conversely a larger velocity in perspective, the wavelength is going to be extremely small for large size objects, so that study we're going to refer to as classical mechanics. That's going to be the study of larger objects. But if we're dealing with something of the electron size, that mass is going to be absolutely small. So that means our wavelength is actually pretty reasonable. Because it's reasonable, we can now actually impart that particle wave duality, which opens up our quantum mechanics.